name is Nicholas Sheely, and I'll be presenting Lab 3. So some physics principles we use in the experiment is that the magnitude of the magnetic field proportionally changes to the distance it is away from the object. In our lab, our goal is to study the magnetic field of a bar magnet with our phone at different distances to find the separation distance ratio that impacts the magnetic field. So in this lab, we measured the distance dependence factor n, the magnetic moment mu, and the magnetic field at 45 degrees. And I concluded that the distance dependence n equals -3, the magnetic moment mu equals 2.9 amperes, and the net magnetic field at 45 degrees for the experimental was 4.83 times 10 to the -5 Tesla, and the computational model was 2.00 times 10 to the -5 Tesla. So a factor we have to take into account when conducting the experiment is that we have to include the Earth's magnetic field, so that the bar magnet has to be placed perpendicular to the Earth's magnetic field. So some of the equations we used in our experiment was the Biot-Savart law, the distance dependence equation, and the linearization formula. So the first thing we did was to locate the magnetometer chip in our smartphone. We moved the bar magnet at different distances and then recorded the distance at the different values we found below. Using the spreadsheet, we calculated the distance dependence value n and then the magnitude of the magnetic moment mu. So the yellow boxes are where I entered in my data, and the equation on the right is important, as the next slide I will compute n and mu. So from the distance dependence, we can conclude that the magnetic is inversely proportional to the cubic distance. And the magnetic moment can be calculated by setting the distance dependence equation to the modified Biot-Savart equation. The value k can be computed by raising e to the natural log of k in the graph. Then the magnetic moment for mu equals 2.94 amperes. So in part 2, we're supposed to move our phone until it reads 100 unitesla. Then, at the perpendicular distance, record the y component and the magnetic field. After, without rotating the phone, move the phone upwards by the same perpendicular distance, resulting in the phone being in a total distance d from the magnet. At 45 degrees, record the x, y, and z components and then adjust it considering the Earth's magnetic field. Then repeat the procedure 3 times and compare the average results to the computational model. So as you can see, the average experimental vector had an average distance of 2.285 meters and is 2.17 times 10 to the -6 in the x direction, 2.2 times 10 to the -5 in the y direction, and -4.29 times 10 to the -5 in the z direction, Tesla. And in my model, the 4 cyan arrows represent the electric field's perpendicular distance, and the 2 orange arrows represent the electric field at 2 on-axis locations. As you can see in the code, the magnetic field is correctly 1/2 the magnitude of the on-axis magnetic field at a distance of 0.285 meters, the magnetic field in 45 degrees, which is 5.42 times 10 to the -6 in the x, 1.927 times 10 to the -5 in the y, Tesla. So in the experiment, we calculated the magnetic field at 45 degrees with an average of a distance of 0.285 and 2.17 times 10 to the negative 6 in the x direction, 2.2 times 10 to the negative 5 in the y direction, negative 4.29 times 10 to the negative 5 Tesla with a magnitude of 4.83 times 10 to the negative 5 Tesla. And in the computational model, the magnetic field is 5.42 times 10 to the negative 6 in the x, 1.93 times 10 to the negative 5 in the y Tesla with a magnitude of 2 times negative 5 Tesla. And the difference are the x direction is about double the computational model, and the experimental calculation has a z direction while the computational model does not. So in conclusion, as the magnetometer moved further away from the magnet, the x direction of the magnetic field measured a near zero. As the magnetometer moved closer to the x direction, the magnetic field increased. If I had not included Earth's magnetic north in the experiment, the results would not be accurate, as the magnetic field would include Earth's magnetic field too. So if we were to stick each bar magnet end to end and run the experiment again, the measurements would be greater because the magnetic field would be stronger. Thank you.